Here we have the Norland CentrocGP for measuring eccentricity on connectors, and this one has the special tunable mount. Certain connectors are designed to be tunable in place, where they have the ferrule has 6 keyways on it that it can be disengaged by pressing on the ferrule and rotating to the appropriate position and snapping back into place. Here we're going to show how the connector is first measured for eccentricity and then how we are going to tune it. So here we insert the connector into the LED port for the illumination, and then we take the connector that we're going to measure and insert it into the mount. So it starts out with the connector in the 12 o'clock position with the key on the connector at 12 o'clock. If we look at the screen here, what we see is the illuminated core and the dark fiber in the center of the screen. So we're going to take the connector and we're going to rotate it and measure it in 4 different positions. So starting in the 12 o'clock position, we're going to measure it once. Then we're going to rotate the connector, measure it a second time, rotate it again, measure it, fourth time, and then we bring it back to the 12 o'clock position and measure it one final time. So here we see the eccentricity measurement. The actual number is 0.39 microns of eccentricity. If we look at the endpoint, which is in blue, since we have the 4 initial measurements and then the final measurement is in blue, this shows us where the eccentricity is on the ferrule with the keyway in the 12 o'clock position. So what this means is that we have to rotate the ferrule about maybe 60 degrees, that you have 6 keyways in it, so you have 6 possible positions to rotate it. So we need to rotate it to the second position over about 60 degrees. So that's what we're going to do here. Is we're just going to push the ferrule in and then rotate it approximately 60 degrees, and then have it snap back out into position. So now when we take this connector and measure it, we're going to bring the connector back into 12 o'clock position, and we're going to measure the connector now. As we've done before, measure it in 4 different positions, rotating it each time. And here we have the results with the eccentricity now in the 12 o'clock quadrant, so that this is now a tuned connector. As you saw on the screen, that the core barely moved visibly. That's because we're able to measure submicron changes in the position as we rotate the connector. Here we see the 5 measurements, and each one shows a fairly repeatable positioning of the eccentricity. As we said here, the measurements of the eccentricity, in this case it's 0.4 microns, 0.40 as opposed to 0.39 before, but it's within 1/100th of a micron, which is pretty accurate. So now this connector is tuned within 60 degrees or within 90 degrees. It's considered a tuned connector. The ferrule cylindricity, which is seen by the repeatability of the measurements of the eccentricity, that all 4 measurements, all 5 measurements fall very, very close to the circle that is calculated. So the cylindricity is considered to be 0.14 microns, which is the max to minimum difference in measurements made in the eccentricity. So for light loss, this connector, if it was, because it's single mode, at 1310, the estimated light loss on this connector would be 0.03 dB, and at 1550, the estimated light loss would be the same, 0.03 dB. And this is based on the idea that all your light loss is based on how the cores align. If this was to be mated with a perfectly centered fiber, that you would have that much light loss. So this shows you a very simple technique to tune fiber optic connectors and tune them very accurately.